Welcome back, Peter, to the second part of the simulation methodology tutorial. Thanks for coming back.
Thank you very much. So this is round 2 of simulation methodology and overview. So what I'm going to talk about in this session is what I refer to and what many other people have now come to refer to as efficiency improvement techniques. But if you've read the Monte Carlo and simulation literature, you'll often hear the term variance reduction methods or variance reduction techniques. This is basically the same set of ideas, but expressed in a somewhat broader view. And I'll talk about the sort of slight difference in emphasis between variance reduction and efficiency improvement a bit later in this lecture. Then I'm going to talk about some specific efficiency improvement techniques, control variates, common random numbers, importance sampling. There are many, many other such methods available within the Monte Carlo simulation communities. Then I'll talk about gradient estimation that obviously relates strongly to the world of stochastic optimization, and I'll finish with some quick discussion about stochastic optimization. All right, so efficiency improvement techniques. We're all thinking about algorithms. Oftentimes we'll have a choice as to which algorithm we may wish to use to compute a particular quantity, let's say alpha, in the context of simulation of Monte Carlo. So it could be that we have algorithm number 1 that gives rise to a sequence of iterates alpha n converging with probability 1, let's say, to alpha, and a second algorithm that gives rise to some beta n's. And then we want to use, obviously, the algorithm that converges faster, that's computationally more efficient. And, as we discussed in the last lecture, it's standard within the Monte Carlo and simulation communities to use limit theorems to study rates of convergence questions. So this is not a community that tends to focus on hard error bands. And in this setting, let's just assume that we have central limit theorems for both algorithm 1 and algorithm 2. And let's assume that they're of the same type that you sort of often see in the world of Monte Carlo, namely square root convergence with a normal distribution on the right-hand side. So algorithm number 1, alpha n minus alpha when scaled by square root of n converges to a normal 0, 1 with standard deviation sigma 1 sitting out in front of them. And similarly for beta n, of course, as we saw in the last lecture, these two limit theorems are asserting that alpha n and beta n converge to their respective limits at square root convergence rate, and with proportionality constants sort of measuring the instance-dependent convergence rate characterized by sigma 1 and sigma 2. So if we just unpack those two limit theorems, and they suggest that alpha n and beta n for large n look like normal random variables having mean alpha, but with different variances. In one case, in the case of alpha n sigma 1 squared over n, in the case of beta n sigma 2 squared over n. And it seems quite natural, if you have a limit theorem of that type, to choose algorithm 1 over algorithm 2 if the variance corresponding to algorithm 1 is smaller than the corresponding variance for algorithm 2. So this approach to choosing and constructing estimators is based on variance, and when we try to construct an estimator that has smaller variance than the current algorithm's variance, we are said to be implementing a variance reduction of some kind, and the class of algorithms are known as variance reduction techniques. So again, if you search under variance reduction technique within the world of simulation and the world of Monte Carlo, you'll come to an enormous range of different ideas that have been developed over the years depending on the
Peter,
communities that are involved. Yes.
yeah, just a quick note. Of course, this assumes that the cost of simulation is kind of similar across these two methods, right? Because I could use method 1 and simulate more and reduce variance that way. That's kind of like silly.
Well, I thank you so much for saying that, because you've set me up for my next slide.
Okay, good. Yeah, all right.
Each iteration of alpha n could be much more costly than an iteration of the second algorithm. So you really need to look at something that takes into account the work required to compute one estimator versus the other. So that you can do by accumulating the total computer time required to compute alpha n and correspondingly beta n. So call T1 of n the total computer time for estimator 1, T2 of n the total computer time for estimator 2 to compute alpha n and beta n. And then you can look at something that is objectively an appropriate metric on which to look at quality of estimators. Namely, let's look at the total computer time budget, C, and let's look at, within a given computer budget, C, which of the two algorithms behaves best. So in view of that perspective, we want to look at the estimators that are available after C units of computer time have been expended. And of course, the value of n that we'll get to within a computer budget C may be a random variable itself. In particular for algorithm I, and I of C will be the maximum n that we're able to get to within computer budget C. And now you can look at the estimator available after having expended C units of computer time. That'll be alpha of C for algorithm 1, beta of C for algorithm 2, and study the convergence rate of those two quantities. So in many settings, there would be some kind of law of large numbers for Ni of C. The total number of iterations that you were able to complete within C units of computer time. And so for example, the law of large numbers might say that Ni of C divided by C converges to some positive constant lambda I. So lambda I is basically the rate at which we compute iterations per unit of computer time. And then it's typically relatively straightforward to convert the two limit theorems that we developed earlier, in which the time index was number of iterations. That doesn't take into account this issue having to do with the cost per iteration of one algorithm versus the other. And now we're doing something that is work normalized. And those two limit theorems now convert to limit theorems involving alpha of C and beta of C. And now we see on the right-hand side a more complicated variance parameter having to do with the product of lambda 1 is a minus 1/2 and sigma 1 for estimator 1 correspondingly for estimator 2. So based on having C units of computer time available, we obviously want to choose the estimator which is better. And now we would choose estimator number 1 over estimator number 2 if its corresponding variance parameter is smaller than the second one. Now in the case where the estimators are obtained by just taking sample averages of IID quantities, that's the sort of plain vanilla Monte Carlo context. So then the alpha n would just be, let's say, an average of some WIs. And then just to be clear in that context, sigma 1 would just have been the variance of sigma 1 squared would just have been the variance of W1. And lambda 1 inverse, that would just be the expected amount of computer time tau 1 required to generate the random variable W1. So this figure of merit down here in this context would be the product of the expected time to generate a W random variable multiplied by the variance of a W random variable. And then you would choose the algorithm that has the smallest product. So you can see from this analysis that when you look at a work normalized analysis as we have here, you don't necessarily want to go for the smaller variance estimator. You want to look at the product. And there are actually even some settings where you can get such a significant reduction in the expected time required to generate the random object W that you're willing to use a W that has a slightly or somewhat higher variance, because this thing is reduced so much that even if the variance goes up somewhat, you're comfortable with it. So what we really should be focusing on is not variance reduction, but reducing this work normalized quantity. And as a consequence, rather than thinking about variance reduction, we really should be thinking about efficiency improvement, by which we mean trying to reduce this product. Now, one important distinction between the world of simulation and the world of statistics is the following. Both literatures and both sets of ideas focus on using samples to estimate things. But there's a very, very important difference between statistics and simulation. In the world of statistics, you sample because you don't know the underlying population. Of course, in the world of simulation, we have algorithms available to actually generate samples from the given population. So we may not be able to write down easily the probability distribution of the particular quantity that we're trying to compute, but we know it implicitly because we have an algorithm that generates random variates from that particular distribution. So in the world of statistics, one sample because you don't know P. In the world of Monte Carlo, all that you're really doing, as we discussed in the last lecture, is you're taking samples basically as a computational vehicle for computing a high-dimensional integral, basically a computational vehicle for computing an expected value. So the world of simulation is really a class of numerical methods that are intended to offer efficient computation of expected values and probabilities. That means in the simulation context that in principle, we know the underlying probability distribution that we're working with. And as a consequence, we can try to leverage the knowledge that we have of that underlying probability distribution to try to obtain efficiency improvements. So pretty much all of the efficiency improvements that you are able to generate within the world of Monte Carlo, what you're effectively doing is using problem structure that is built into the particular computational environment that you're dealing with to improve the rate of convergence. So the more problem structure that you have available, the better you should be able to reduce variance. And that is one of the things that makes this a particularly interesting part of the world of simulation, the world of Monte Carlo, is trying to be creative with how you develop and how you exploit particular problem structures. All right, so let me talk about, start with one of the most simple of all variance reduction methods, but one that is very, very general, applies in many different contexts, and often can be quite powerful, quite useful when appropriately applied. So again, we're going to start off with the goal of trying to compute a particular expected value. We're going to compute the expected value, let's say, of a random variable W. And suppose that we have some random variable Z with a known expectation. Now, it's always the case in any simulation context that there are many random variables lying around for which you have known expectation. So in particular, we all know that the randomness that we use in a simulation environment typically derives from underlying uniform random variables. And we certainly know what the expected value of a uniform random variable is. So we have, quite obviously, lots of input quantities that go into our simulation that have known expected values. So assuming now that we have a random variable Z available to us that has a known expectation, we can center that random variable Z, subtract off its expected value because we know what expected value of Z is. That gives us a random variable C that I'll call the control variable, the control random variable. Now you can look at the random variable W of lambda, which is given by the original W minus some constant times the control C. And we see that if you look at the expected value of this quantity, well, C has mean 0 because C is the centered Z. And as a consequence, expected value of W has expected value of W lambda has exactly the same expected value as W itself. So we haven't changed the expected value whatsoever by subtracting off lambda C. But by subtracting off lambda C, potentially we can judiciously use the correlation between W and C to get a variance reduction. So let's see how that works. If we compute the variance of W of lambda, we get variance of W minus 2 times lambda times the covariance plus lambda squared times the variance. That's quadratic in lambda, easy to minimize. And the minimizing lambda star is given by the covariance between W and the control C itself divided by the variance of C. When we plug in that minimizing value of lambda star, it turns out that the minimizing variance is exactly the variance of W that we started with, that you would have had if you didn't apply a control variate, times 1 minus rho squared, where rho is the coefficient of correlation between W and C. And this says, of course, that the closer that rho is to either +1 or -1, the larger a variance reduction you will get by applying this particular methodology. So if you can get a strong correlation, whether it be positive or negative, just so long as they correlate strongly with one another, control variates can give a very significant degree of variance reduction. Now, of course, in practice, since we don't know the expected value of W, we don't know the variance of W, we don't know the covariance between W and C, so this lambda star is unknown in general. But as with many things in the world of Monte Carlo, we can internally estimate these parameters from the sample itself. In particular, we all know how to estimate the variance of a random variable C through its sample variance. And there's a corresponding sample covariance that can be used to estimate the population covariance between W and C. And if you plug in those sample estimates, then we get a quantity lambda hat n. And then we can imagine using the estimator W bar n minus lambda hat n times C bar n as our estimator of the quantity alpha. And if we apply this particular control variates approach, we would expect, since for n large, since lambda hat n converges to lambda star almost surely as n goes to infinity, for large sample sizes, we might hope that its variance behaves pretty much the same as if you had known the correct value of lambda star from the beginning. And indeed, that's what happens in this particular case. Is there's going to be a central limit theorem for this quantity, and the central limit theorem for this random variable will look exactly the same as the central limit theorem in the case that you had known the optimal control parameter from the beginning. So as a consequence, this is a relatively straightforward method to apply, and you can get significant variance reductions. In many cases, it's typically close to being costless. And when you put together a simulation, it doesn't cost much to collect both the sample mean of the CIs along with the sample mean of the WIs. And computing the lambda hat n at the end is also relatively costless relative to actually generating paths of the underlying system itself. So oftentimes this is a pretty cheap thing to implement. You'll pay very little cost in terms of increase in the computation time, and there'll be more than enough variance reduction to make this worthwhile. Now, the control variance method that I just described is a control variance scheme involving a single control, but we could have a vector of controls as well. And then the lambda becomes a vector of control coefficients that have to be optimally estimated. And again, that is relatively doable. You do run into problems, as you would expect. If you choose the number of controls to be too large, then basically you will not have enough data available to accurately estimate the covariance structure, and you could get some bad things happening as a consequence. But if you limit the number of controls that you use to ones that are have strong correlations, then the vector valued version of this algorithm can also work quite well and quite effectively. So I'd like to illustrate this idea in the context of Markov chains, and I'm going to introduce another idea related to so-called Martingale controls. This is something that I looked at with a PhD student of mine, Shane Henderson, and Sean has also been involved in doing research on this particular class of ideas. So let me just illustrate this methodology in the context of trying to compute an expected infinite horizon discounted reward. So we're going to try to compute this expected value starting from state X. And of course, if I look at this expected value as a function of state X, that gives me a function u star that depends on the particular starting state X. And probably we all know that this u star satisfies a particular system of linear equations. In particular, if we write u as a column vector in which the X entry is u star of X, then u, that column vector, satisfies as equal to the reward vector R plus the discount factor of the minus alpha times Pu, where P is the transition matrix of the Markov chain. Now, it turns out that this random variable mn, if I look at this as a function of n, is what is it? The right-hand side is basically the sum of the discounted rewards up to time n minus 1 plus a discounted down version of u star of xn, and u star of xn is basically the cost to go, or the reward to go from the random state xn that we're in at time n. And this mn turns out to be a Martingale. So what is a Martingale? Martingale, of course, is a sequence of random variables having the property that its conditional expectation at time n plus 1, given the history of the chain up to time n, is exactly the value of the Martingale at time n. So that is defines what we call a Martingale. And of course, one implication of that is that if I take the expected value of both sides of this equation, I can conclude that expected value of mn plus n, n plus 1 is equal to expected value of mn. In other words, Martingales have the property that the mean doesn't change over time. So Martingales were first used in conjunction with exploring gambling systems, and this would correspond to the fortune of a gambler in a fair game. His or her fortune would have no tendency to either increase or decrease in expectation over time. So that's Martingale. And of course, the consequence of this is that the mean doesn't change as a function of n. So mn minus m0 has expected value 0. So that is a potential control that we can use according to the control variates philosophy that we discussed earlier. Now, if I put lambda equals 1 in this particular example, and I look at w minus lambda c infinity, so c infinity is m infinity minus m0. M infinity is this quantity right here with n put set equal to infinity. And with n set equal to infinity, this discount factor here makes this second quantity 0. And this first quantity is just the infinite sum. So m infinity is exactly equal to this infinite sum up here. And m0 is just u star of x0 itself. So we're looking at c infinity as just this infinite sum minus the u star value at the initial state. So when you look at w and subtract off lambda times c infinity with lambda equals 1, you just get back u star of x itself. U star of x, of course, is deterministic. So we actually get variance of w of lambda with this choice of lambda equal to 0. So this is a zero variance method. It would be great if you could actually apply this in practice, but of course you can't apply this in practice because you don't know the u star of x function. After all, the u star of x function is what we're actually trying to compute with this simulation. But what this suggests, and this is a philosophy that we will use at least one more time in this talk is if you don't know something, at least hope that you can find, for example, an approximation to that U star and use that instead. So, so what this analysis suggests is let's try to find a U tilde that's a good approximation to U star. If we can do that, then we're going to use this martingale instead, involving the U tilde in place of U star and involving an R tilde instead of the original reward function. And what is the R tilde? The R tilde is just what it needs to be in order for U tilde to satisfy the same type of linear system that we discussed earlier for the original problem, which means in particular that the U tilde function can again be represented, can again be viewed as being the infinite horizon expected value discounted against rewards that are no longer given by the original rewards R of X, but are given by this modified rewards R tilde of X, where R tilde is given by this quantity. All right, so that gives us suggests a way of using a good approximation. If the approximation is good, then one would hope that you can get very strong variance reductions, because we know that if you chose exactly the right choice of U star, you'd actually get variance 0. Well, in practice, obviously using approximation, you're not going to get variance 0, but we hope that you get something that is significantly reduced relative to the standard plain vanilla estimating. All right, so that's an illustration of control variates and its application to in the context of Markov chains, in particular in the setting of Martingale controls. Now, by the way, this approach that we used here to construct a control variate applies in many, many other settings as well, not just infinite horizon discounted rewards, but basically any expected value of probability in the world of Markov chains for which there is a linear system of equations that defines that expected value or that probability. That would be something that would be amenable to the same kind of Martingale idea to establish variance reductions. All right, so let's turn now to another common variance reduction method. In fact, the method of common random numbers. And let's talk about how that would apply in the setting in which we have, for example, two policies that you want to compare. And policy number 1 gives rise to a random variable that I'll call W1. And policy number 2 gives rise to a random variable that I'll call W2. And we're trying to compare the expected value of W1 versus the expected value of W2. Of course, in doing the comparison, we'd like to look at is expected value of W1 bigger than expected value of W2. We'd probably also like to know the magnitude of that difference. So we're trying to compute the difference between kappa 1 and kappa 2, kappa I being expected value of WI. Yeah.
Just for the previous method, multiple of us are wondering about, so if P is, I mean, you presumably have a simulated Markov chain, but in the definition of R tilde, you have to apply P to U tilde, which if you have a high dimensional state space or like a large state space in general, I mean, like, how do you calculate this R tilde? You would need to know the values of R tilde and the trajectory to be able to calculate this variance reduced estimate. So what shall we do? Or like what should we be thinking about? What's happening here? How do we make this a functional procedure?
So there are settings where you can do this quite readily. So you know, the Markov chains in which we have a stochastic recursion of this form, where the ZIs have a nice, well-known distribution. And it wouldn't be hard in that context to compute this quantity, right? It would just be in that setting P.
Roll it a little bit more.
Pardon me?
Simulate.
In that context, it would just be p u tilde of x.
Oh, okay. And so maybe U has also some nice analytical form, and the distribution has some nice analytical form, and
Yeah,
sometimes.
Right. So in some modeling context, for example, when you're using simulation in the context of performance modeling, okay, there we go. Then it would often be the case that you would know exactly what the G function would be, and you'd know exactly what the distribution of Z would be. And this wouldn't be a hard thing to do. Now, in the reinforcement learning context, where you don't have this type of explicit structure, you're absolutely right. This is a significantly harder thing to implement in that context. And I would say that's probably an open research question as to whether this can be practically useful in that setting.
Okay, yeah, good. It's good. It's very good to know that this is how the fields are kind of looking at similar problems but slightly different settings, and then different things make sense.
Right,
Yeah.
exactly. So, you know, in some settings, doing this calculation is quite viable. In other settings, and I think you pointed out, you know, it is the case that I think in the RL context, this would be a harder thing, significantly harder thing to think through how you could implement this effectively.
Yeah, makes perfect sense.
Great question. Okay, so let's talk about, to go back to this common random numbers issue, we're trying to compare two different stochastic models, corresponding to two different policies. And obviously, in estimating alpha, the most natural thing to do is just to estimate the expected value for policy one through a sample average, correspondingly also for the second policy. Now, one thing that's important to recognize is there's no reason that we need to use exactly the same sample sizes N1 and N2 in comparing these two systems. And when you make that observation, make that realization, that leads you into the world of what would be called stratified sampling. So how much computational effort do you want to devote to policy one versus policy two? But you'd imagine somehow that that would have something to do with how variable W1 is versus W2. And indeed, there's a optimal choice for how much sampling you should do of one stratum versus the other, of system one versus system two. And it turns out that the optimal sample size scales in proportion, by the way, not to the variance, but in proportion to the standard deviation. So you ought to choose Ni proportional to lambda I minus 1/2 times sigma I. Of course, N1 plus N2 has to be equal to the computational budget that you have available. So that's efficiency improvement technique one. Efficiency improvement technique two is what people would call the method of common random numbers. So in the first efficiency improvement technique, you're free to use different sample sizes because all of the samples that we use for estimator one are independent of those for estimator two. And since these are completely decoupled calculations, I can run a bigger sample size for one than for the other. But another thing that you could do is you could pair up the W1 simulations with the W2 simulations and then try to correlate the W1s and W2s from each successive set of experiments. Now you'd have to choose the sample sizes equal because you're pairing up W1 and W2 in every experiment that you do, in every simulation that you do. Now you try to construct a joint distribution supporting both the random variable W1 and the random variable W2 that has the following nice property, namely if you look at the difference between W1 and W2 and you compute its variance, well, you're obviously going to get the variance of W1, the variance of W2, and here's where the joint distribution comes in. These two quantities obviously just depend on the marginals, but the joint distribution comes in through the covariance between W1 and W2. You want to make the variance of W as small as possible, which means that you want to make this covariance between W1 and W2 as large as possible. You want to correlate this to be as big as possible. And this again involves choosing a suitable joint distribution that induces as much positive correlation as possible. So this is unlike the control variates context where you've got variance reductions for both negative and positive correlations. In this setting, you really need the correlation to be strong and positive. So here's a setting where it's relatively easy to do. So imagine that W1 and W2 are monotone functions of some input randomness, C1 through CD, where the f tilde 1 function and f tilde 2 functions are both monotone in the same direction. So in other words, if you look at f tilde I as a function of its d coordinates, the f tilde i's are monotone in each of the different coordinate variables. So the f tilde i's are monotone in that sense. Then there's a general theorem having to do with what are called associated random variables, that W1 and W2 are guaranteed to have a positive covariance in that case. And as a consequence, you get a guaranteed efficiency improvement in this context. So this is a setting where you have to be creative in terms of finding a coupling, finding a joint distribution that induces as much positive correlation as possible. And again, in settings where you can do this effectively, this can provide quite significant variance reductions in looking at differences of expected values. So intuitively, it makes sense that you get a variance reduction by doing this, because at some level, by subjecting W1 and W2 to exactly the same input randomness, this is fairer to the two systems. If one system is unlucky enough to get some bad CIs that make it small, that same set of random variables C1 through CD will also make W2 small, so they'll both simultaneously be lower than average, and you won't get any sort of quote-unquote unfair comparisons between W1 and W2. So it makes sense intuitively that inducing this type of correlation would generate a variance reduction. Okay, next algorithm is importance sampling. So suppose that we want to compute the expected value of W. In many contexts, we have the opportunity to potentially use a different sampling distribution Q by modifying the underlying probability distribution P. In particular, let's say multiply and divide through by the density of P with respect to Q. This would be the so-called likelihood ratio that I'm denoting here as L of omega. And then we can write this P expected value in terms of a Q expected value, in which W is now multiplied by L. L is a likelihood random variable that basically measures the corresponding likelihood of a given omega under P to that under Q. That's why it's called a likelihood ratio in the world of statistics. So with this identity in place, we can now search for a value of Q that, for a choice of Q that makes the variance of this estimator of the expected value as small as possible. And there is, in fact, is a zero variance choice in the case that the random variable W is non-negative. Turns out in that case, if I just choose the likelihood ratio, or equivalently, if I choose Q to have the following likelihood ratio, namely to make L star equal to W over alpha, then you actually get a output random variable W times L, which is equal to, which I don't quite have this correct. It'd be the other way around, should be alpha over W. And then if you take W times L star, we see that we just get alpha back again. That's a deterministic quantity, namely the expected value we're trying to compute. This is another situation where we get zero variance. So just as in the control variates context, this is a setting where it's unrealistic to expect that you can ever implement this zero variance algorithm in practice. But of course, just as in the previous context, you hope to use a distribution Q tilde that at least approximates Q star. And there many algorithms have been successfully built exactly on that kind of principle using the ideas of importance sampling. In particular, in the world of rare event simulation, importance sampling turns out to be a very, very powerful method in getting potentially enormous variance reductions for rare event probabilities. Now, let me just illustrate this importance sampling idea in the context of Markov chains. Suppose that we want to compute the expected reward associated with the state of a Markov chain at time n. The natural importance distribution Q to use would be one under which the dynamics of X continue to be determined by a Markov chain. So effectively, we replace the transition matrix P by a transition matrix Q and use Q dynamics to run the Markov chain rather than P dynamics. And when you do that, you get a likelihood ratio that is just the product of the P transition probabilities for a given path divided by the product of the Q transition probabilities for the same path. So the product of the numerator probabilities is just the product of that path associated with the P distribution, and similarly the product of the Q probabilities in the denominator is just the relative likelihood of that sample path under the Q dynamics. Now, it turns out the variance of this type of likelihood ratio deteriorates quite badly as a function of the time horizon n. In fact, it increases geometrically or exponentially in n. But an important thing to recognize, and maybe a surprising thing to recognize, is that if you look at the ln itself, and the easiest way to look at ln is, well, in the world of probability, it's sums of random variables that are easiest to analyze because we have laws of large numbers and central limit theorem. So ln is a product. But if we take the log of ln, we do get a sum. So if we take log of ln, we get a sum of quantities involving the path dynamics of the Markov chain divided by n. Then we're going to be basically looking at a law of large numbers for Markov chains. Laws of large numbers for Markov chains apply in great generality. And what one sees is that you end up with a entropy type limit in which this entropy quantity is less than 0. Now, what's that saying? That's saying the log of ln divided by n converges to a limit that is less than 0. And of course, that's basically saying that ln decays to 0 exponentially fast in n. So not only does ln go to 0, Q almost surely, other than you apply the dynamics of Q, but it even goes to 0 exponentially fast in n. So ln is going to 0 exponentially fast, but up here, the variance of ln is exploding to infinity exponentially fast. So that's a bit of a strange dichotomy there. But of course, that's consistent with the following type of situation, that if you look at the density function associated with this likelihood ratio, it's when n is large, it's accumulating a lot of mass near 0. But of course, in order for the variance to be big, it must be that there's some probability mass out at some very large value that makes the variance of ln go to infinity exponentially in n. So this is a situation where the likelihood ratio is very heavy-tailed, and as a consequence, importance sampling has the following very unpleasant characteristic. Namely, variance reduction can work very effectively in many settings, but there are also many settings where the importance sampling can look to the naked eye like it is behaving very well. And what do I mean by look to the naked eye? You form a sample variance estimate, And what happens when you form the sample variance estimate? Well, you're mostly sampling from this part of the distribution, and the likelihood quantities that you're sampling from are all close together, all close to zero. So as a consequence, the sample variance estimate that you get is very small. And as a consequence, the sample variances that you get for the importance sampling algorithm look very small, which means you say to yourself, this is great, I'm getting a big variance reduction. But in fact, what could very well be happening is that you have a disaster occurring because you just haven't sampled these pieces. And those are pieces that could be quite fundamentally important to the expectation that you're actually trying to compute. So when importance sampling fails, it fails in the worst possible way, namely the standard sample-based diagnostic that we would use to determine whether an algorithm is behaving poorly or not, the so-called, our standard sample variance estimate, that also goes to pieces in the problems where importance sampling tends to behave the worst. So you have to be very careful in applying importance sampling ideas to problems in which the time horizon n is large. I should mention that you might imagine, based on the fact that when you look at 1 plus constant over n to the nth power, this is looking for large n like e to the c. This is all something we know. Now, where is this, something like this coming up? Something like this is coming up basically when we look at the likelihood ratio. You might imagine, based on this analysis, that you need Q and P. If you want to avoid this exponential increase in the variance, you want to choose P and Q relatively close to one another. So you don't want to have a Q being a large perturbation away from P. And you might say to yourself, well, this analysis suggests that Q and P have to be perturbed away from one another by an amount of order 1 over n. Turns out you can actually use a 1 over root n perturbation, and you still get the fact that the likelihood ratio, when you perturb in that way, no longer blows up exponentially, but is well behaved, even for large time horizons n. And the reason that this 1 over root n works rather than 1 over n has to do with the fact that the likelihood ratio is again a Martingale, and there's something related to some behavior that is coming out of the Martingale central limit theorem that is controlling the cycle fluctuations of the likelihood ratio.
Peter,
Yes.
there are a number of questions. So one of the questions is, okay, so what does this all mean? So if you want to use importance sampling, what would be the recommendation? How do we determine the horizon after which we shouldn't even attempt to apply it? What would you do?
So, I think what this analysis says is that you have to have your eyes open when you apply importance sampling. And you can do various things to try to control these bad fluctuations. Now, when you do that, you're also going to limit the degree of variance reduction that the variance reduction technique might have otherwise given to you. But, so, for example, and you would see, and one diagnostic, one thing you can certainly do that can often help is likelihood ratios must have the property. If we look back at this identity, if I put W equal to 1 on the left-hand side and the right-hand side, then I see, of course, on the left-hand side, I get 1. On the right-hand side, I get expected value of L under Q. So I know that expected value of the likelihood ratio under the Q measure is 1. And so if I am using importance sampling and I find out that the average of my likelihood ratios is close to 1, that's a good thing. That means I probably, even if I'm in a situation, as I see here, where most of the mass of the likelihood ratio is close to 0, it must be that I've done enough sampling with my importance sampling distribution to have seen some of these observations out in the tail. So that would mean that I've got a large enough sample size of importance experiments that I've done that I've seen some of this stuff. And now I think in that situation, you would worry much less about the sample variances and things of that kind. It's very likely that the sample variance is then going to be a reliable estimate of the true population variance if you're seeing this type of behavior. If you see the sample average L bar is not close to 1, that's probably, again, a very strong indicator that you haven't yet seen this part of the tail, and that the sample variance estimate that you have is potentially misleading.
In fact, I suspect that this is like a one-sided test, right? That if you're seeing that the sample average is far from 1, then you can be sure that something is fishy. Whereas if you see that the sample average is 1, then maybe other things can still be fishy. It's just you're lucky somehow.
Well, it feels like that. And I totally, I think in many problems what you said is correct, but it wouldn't always be the case, because there would be problems. For example, and this can happen in the rare event simulation context. There would be settings where the W may have support on a part of the probability space, on part of the sample space, where this doesn't occur, where you don't actually have this big piece out in the tail. So it could be that the event, for example, you're trying to compute a rare event probability for, is an event where the likelihood ratio is uniformly well controlled, and all of its values are actually down here, so that you actually get an extremely big variance reduction. And that, in fact, is what happens in a typically successful rare event simulation context. Is that's exactly what occurs. Is the likelihood, the part of the likelihood ratio where the expected value is where it's big, that makes the expected value equal to 1, just has no intersection with the event that you're actually trying to compute a probability for.
Yeah, okay, gotcha. So this one-sided idea is also imperfect in a way. Even if you see a big deviation with a bar, it may not matter because you may be lucky.
Right, I think it depends a lot on the type of, if you're trying to compute, so for example, expected long-run reward, and you decide to use importance sampling to try to estimate that, that would be a situation, I think, where your diagnostic, your one-sided perspective would be more accurate in that setting than in the rare event simulation context.
Awesome. And so when you're talking about this controlling Q and P to be close to each other, what are the methods that people would use? Would particle filtering, someone asked, would particle filtering be one of the methods that could, like make you adapt the sampling distributions to that, like this quantity is controlled?
I haven't seen particle filtering applied to do this, and there would be, but it is the case that particle type methods can be quite efficient in some settings where importance sampling is also potentially effective. So for example, again, in the rare event simulation context, it would be the case that sometimes it's actually better to apply a method called splitting. And splitting is, at some level, basically a particle method for doing rare event simulation. So I like the idea of thinking about particles. I'm not sure that I've seen it in exactly a context where it's been used to try to
around. I think that they did have some adaptive Monte Carlo, but maybe I'm mixing this up with particle filters. I don't know. Anyways, it's all good. Thanks.
Okay, great. So I'm just going to continue. Can I take a few more minutes? I see it's 3 o'clock.
Yeah.
So I just want to say a bit about gradient estimation. And So we all know that there are many settings in which you want to compute gradients. And it's important to sort of recognize that there are two ways that gradients can appear in these integration problems. One is that the performance measure W depends explicitly on the parameter that you want to compute a gradient for. The other case is that the parameter appears in the probability measure or probability distribution P theta. And an important thing to recognize is that oftentimes you have the ability to move dependence in P theta into the W thetas and reverse as well. So for example, in the case of normal random variables, we can imagine dependence in, let's say, the mean as either being represented, for example, in the probability density function underlying normal random variable. That would correspond to the dependence on the mean parameter, let's say mu, sitting in the P theta. The other thing that you could do is, you know that normal random variables can be realized with the mean sitting in as a location parameter. So take a normal 0, 1 and add mu onto that. That is another way of representing a normal with a mean mu. And when you push out the dependence into the random variable itself, that would mean that you're sort of looking at parametric dependence in W of theta. Now, computing gradients is of importance in the context of stochastic gradient descent. It's also important in the context of statistical analysis, where you're trying to understand the sensitivity of the performance of your system to statistical uncertainty and underlying model parameters. So when the parametric dependence sits in the W of theta, we can just bring the gradient inside and hopefully interchange the derivative of an expected value. We can do a similar thing in the context of parametric dependence in the probability distribution P theta. In that case, we would apply the importance sampling idea that we discussed earlier to represent the P theta distribution in terms of the Q distribution. Q distribution in this context would be the P distribution sitting at parameter point theta naught. So now we have a representation of alpha theta in terms of the expected value at parameter point theta naught. This would be like the expected value under Q that we're looking at earlier in the importance sampling context, times W times the likelihood ratio. Now, of course, the likelihood ratio depends on the parameter theta. That's how we end up with this representation. Now, again, you can just interchange, or hopefully just interchange, the gradient and the expected value. Now, I should say a little bit here that in general, the conditions under which you can interchange the expected value and the gradient, those conditions are very, very weak in the setting of this interchange. So it's almost always the case that this limit interchange is valid. It's not anywhere near as often the case that you can interchange the gradient with the expected value and the parametric dependence is sitting in the W range variable. All right, so let me now talk about the application to Markov chains. Suppose that we want to compute a gradient of an expected value corresponding to a steady state reward. So think about x infinity as having a steady state distribution, R is the reward function. I want to compute the expected value of the reward under parameter choice theta. And in this case, the natural W would be just the time average reward that I get from simulating the first n steps of the Markov chain. That should be a good estimate of R of x infinity. And now the natural estimator based on the likelihood ratio idea would be to represent the gradient in terms of W times the gradient of the likelihood ratio, and the gradient of the likelihood ratio is easily computable in this context. And Now, again, there's a very nice thing that we observe in this setting because the likelihood ratio itself is a martingale. It turns out it's a mean one martingale. The gradient of the likelihood ratio turns out to be another martingale, and this thing actually has mean zero. So the fact that this thing is a mean zero martingale, by the way, this of course is suggesting, based on our discussion earlier, that this thing can be used as a control variable. So we'll come back to that in a moment. I'm not going to go through the details in this slide because we're short of time, but let me just say that that when the W gradient estimator, so that style of computing gradients would be known within the discrete event simulation community as infinitesimal perturbation analysis, IPA. So in this setting, IPA, infinitesimal perturbation analysis, has an error that decreases at rate 1 over square root of n. So in other words, the standard canonical convergence rate for Monte Carlo, namely errors go down at rate 1 over square root. When you apply the likelihood ratio idea, the errors are much, much larger. Now, it's the case that likelihood ratio methods would be applicable in much greater generality, but along with that greater applicability comes much larger variances, and you can sort of see that through this last line. I'm not going to go through the derivation. You can easily follow, roughly speaking, what I've done in these first two lines. But the key thing that you can see here is that rather than the error going down at rate 1 over root n, the error is actually increasing at rate square root of n, which is pretty not too good. Now, you see that the pre-multiplier in front of the root n involves the expected reward. This obviously goes away if the expected reward is 0. Well, one thing that you might think about doing is try to set up the problem so that the expected reward is indeed 0. And you might think about doing that by working with, instead of working with the reward function itself, try to work with a standard version of the reward function so that this thing would indeed have mean 0. Then this thing would go away. And you'd end up with a variability to this estimator that still wouldn't be going to 0 at the canonical rate, but at least the variability would be of order 1. And that would suggest that then by replicating this estimator multiple times, that you could then get a consistent estimator for the gradient by just doing some super replications of this quantity independently multiple times, let's say m of them. And by averaging those m things, you'd get a gradient estimate that would have a stochastic variability of order 1 over square root of m. So that then is in the realm of something that is practically doable. And you can see that if you do indeed do what I just suggested, that you get improved performance, and the improved performance that I was hinting at effectively is equivalent to using the fact that this gradient is a zero mean martingale, which means that you can represent it in terms of martingale differences. That's the DIs that I have here, and then apply martingale central limit ideas to obtain the limiting approximations that are on these slides. So likelihood ratio gradient estimators can be successfully used in many different contexts, but they do typically have significantly larger variability than do the IPA estimates in settings when IPA and likelihood ratio methods both are applicable. Another alternative method, of course, is to not try to go for computing the gradient, but to use a finite difference approximation. They typically would converge significantly slower than would the likelihood ratio gradient estimates that I was just describing. When you apply finite differences, one thing to be aware of is, just as in the world of deterministic numerical calculation, when you want to compute derivatives or gradients, you always do better by using central difference approximations rather than forward difference or backward difference approximations. So you can, just a very quick sense of what happens in this context. The natural finite difference approximation would be if you want to compute the performance of the gradient at, let's say, the point theta naught, the derivative at the point theta naught. I do some simulations at theta naught plus h, simulations at point theta naught minus h. That's central differences, divide by 2h. And then because of the central differences, the second derivative term in the error gets knocked out, in particular when you do a Taylor approximation of the expected values corresponding to this piece and this piece. And now you get a contribution from the third derivative of order h squared, not of order h as would have occurred if you'd applied forward differences. Here's the random error. The optimal choice of difference increment is of order n to the minus 1/6. So you can use a pretty big difference increment because of the fact that you're doing central differences. And as a consequence of the fact that you can choose an h that's big, that means the quantity that you're dividing through here in the denominator is relatively large, not small. If this thing were small, that really blows up the variance. That gives you a convergence rate of n to the minus 1/3. And if you then did some obvious common random number synchronization, so the random numbers that you simulate at theta naught plus h are closely synchronized with those at the point theta naught plus h, then in significant generality, at least in the context of discrete event simulation type objects, you get a convergence rate that is better than just using central differences. You get a convergence rate of n to the minus 2/5, which is now getting somewhat close to the canonical square root rate. All right, so I'm not going to cover these last two slides in stochastic optimization. You can just read that for yourself. Let me just conclude by saying that the simulation literature and the Monte Carlo literature is an enormous literature. Monte Carlo is applied in pretty much every area of engineering, every area of the sciences, even some areas of the social sciences, economics, etc. Different fields construct somewhat different methodologies depending on the class of models that they typically work with. And so you can find a vast array of interesting and different ideas that people applied in which they have taken advantage of problem structure associated with the models that go with their own particular domain area and have creatively used that problem structure to generate powerful efficiency improvement techniques that leverage that structure. There are lots of things I haven't covered in today's lectures, and I'm not going to mention them at this point, but you can find some discussion of these things in the book that I wrote with Soren Asmussen. You can go look at the Winter Simulation Conference. That's a major conference for people that work in the simulation area. And there's an ACM journal that is devoted to simulation as well. So all of those places are good places to read up on simulation and its various research sub-areas. So thank you very much for listening to me this afternoon. And if you have any further questions, I'll be happy to take them at this point.
Thank you. Very nice talk. Of course, it's really hard to give an overview of all the results that exist in this huge literature, I guess. But I think that I don't know, personally, I really like this overview. It gave us a glimpse into the way people are approaching these problems. So one of the big differences that seems to be true or seems to appear between how machine learning people are thinking about similar problems versus what we see here is this distinct emphasis or lack of emphasis on the part of machine learning people on asymptotics, right? So we know that a lot of times the asymptotics is going to be very useful, but there are also cases when the asymptotics is kind of dangerous. Do you have some high-level thoughts about how to think about this? how important it is to think about the non-asymptotic cases, finite time analysis. This is especially, I guess, interesting if you're trying to come up with, general algorithms for some classes of problems that would adapt to the structure of the problem, and you really care about the finite sample performance. Is that something that people are interested in the simulation community, or is this on a fringe, or?
I think that the simulation community also is being influenced by people's interests on hard error bounds as associated with some areas of machine learning, for example. But it is the case probably that most people would take the view that if you had approached something like the construction of confidence intervals, well, let's imagine the very first community that had gotten into that was a community that was very focused on finite time bounds. It's probably the case, maybe arguably the case, that maybe all of this theory having to do with the use of the normal approximation would not have gotten developed to any appreciable degree, because that theory does not come with good finite sample guarantees. There are things called the variates theorem and Edgeworth expansion and various other things that are suggestive of what happens for finite sample sizes, but those, the variates theorem in particular, which gives you rates of convergence for the central limit theorem, there's no way to get a error rate on the central limit theorem without having information about effectively higher moments of a random variable in the variance. So now you need to know something about, let's say, the third moment of the random variable or the 2 plus delta moment of the random variable. And as I was saying earlier, you would have access to that in the bounded case. Even in the bounded case, once you're outside the Bernoulli setting, you probably begin getting very, very conservative estimates. If you look at the worst 2 plus delta moment over, let's say, a random variable that's bounded between minus C and plus C. So,
I guess it raises the question of how the degree of adaptivity that you can achieve if you're constructing these finite sample bounds, right? Because I agree with you that, like, if you focus on a worst case, then worst case bounds across the board tend to be really conservative. Of course, if they're worst case optimal, that you can't even improve upon them, right? In the worst case setting. So if you take, bounded random variables, then everything is optimal. You can't improve upon it in the worst case sense. But of course, it's going to be conservative. It misses like big things. Bernstein comes along, and so on. So first, the question is like, how far can you push this? And I guess maybe the question is like, how, like, is this something that people worry about or would think would be useful to dive more into, or people for some reason believe that the asymptotic really captures the essential aspects of the problems in a way?
So I'll just, I can't speak on behalf of the entire community. I can only speak on my own behalf. And I guess
you probably have some feelings.
Yeah. I would say that that again, just going back to this, I think the confidence interval methodologies that are based on normal approximations are generally viewed as being extremely useful at both a practical level and theoretical level. And there are diagnostics that you can do that sort of are indicative of situations in which you would have some sense that maybe the normal approximation is not working well in this particular context. For example, if you just look at the sample skewness or sample kurtosis from a sample, and you see that they are significantly different from what you see in a normal population, that would be indicative of the fact that probably the normal approximation and the confidence interval based on normal approximation are probably not going to be doing well for relatively small sample size, in particular maybe the sample size that you've used. And you would see, for example, if you bootstrapped the confidence interval instead, that you get significantly different confidence intervals than what you get from the asymptotic theory. So there are sample-based things that you can do that do give you information about small sample problems that you may be seeing and applying the asymptotic theory. I think that when you look at what statisticians would typically do, that would be their typical answer to those types of problems. They're well aware of the fact that there are issues that arise in small sample settings that cast doubt on the limit theory. But
Yeah, I mean, like, if you think about the Bernoulli and Poisson case, right?
right.
It's probably one of the first things that everyone learns about after the central limit theory, right?
Exactly. So, but people would look probably more for diagnostics that you can see from the sample. Now, in the world of statistics, they really have no choice other than to do that because you know they don't know anything about the underlying population, so they can't assume that they have let's say that they have a bound of 100, let's say, on the population variance. There's no way for statisticians to make that.
Last example, you're thinking about average height of people, then you can say that, okay, biology limits the height.
Yeah. Well, that's you're right. And that'd be a context where you could say there are settings where things are bounded, but
Yeah.
even in those settings, then you could begin arguing: do I really have an IID sample or not in the population?
Sure. Yeah. Yeah. True.
So, the world of Monte Carlo is a setting where, in principle, we can verify all of these hypotheses. We, in principle, do know what the variance is, what
Right.
bound things as we wish. So there is some difference between the Monte Carlo setting and the statistics setting, but I think probably what I said a moment ago, I think would still be accurate. Probably most people who do practical Monte Carlo, and it's arguable about whether I'm in that group or not, but to the extent that you look at people that really are using Monte Carlo at a practical level, I think most of the things that they would do would not be based on finite and theory. Most of what they would do would be based on looking at the sample that comes out of the Monte Carlo experiment and doing some adaptation based on that.
Mm-hmm. Okay, thank you. So there is a question from Gergu. Is the slow rate for finite difference gradient estimators inherent? Are there any lower bounds for this family of estimators? You mentioned the n to the -1/3 and to the -2/5.
Yeah, I think, I haven't thought about that, but my guess is that there are inherent bounds.
Yeah, it's a good question.
Interesting question.
Yeah, you can think about a family of functions. Obviously, it should be some smooth family of functions, and then you want some kind of estimator that is based on finite differences, and then the bias variance should be resolved in some way. And like the question is, how does it resolve? I guess.
I think if you're only allowed to do function evaluations, you have no access to gradients along the lines of the likelihood ratio gradient estimate, but everything has to be based on function evaluations only. And quite confident that there would be reasonable and interesting lower bounds. And I'm sure that they would coincide with what you see in this theory.
Okay,
Yeah.
That's interesting. I find that question quite fascinating. Yeah, Sean yesterday gave a talk where he was talking about quasi-stochastic approximations. He seems to be a little bit obsessed with that. Sean, do you want to say a few words about it? I think it is also related to quasi-Monte Carlo, I guess. And so I guess in his talk, he was emphasizing that quasi-stochastic approximation, where you're replacing the noise that would go into, let's say you have some simulation based on which you run your stochastic approximation algorithm, rather than inducing noise there, you induce some, periodic signal or something like that that has some nice ergodicity property.
Mm-hmm.
And then lo and behold, you find that convergence rate do improve. So that was a major point in his lecture. I don't know what he wants me to ask though. Like he sent the message, but
That's an interesting.
I apologize. I should have done that in hiding. It just with Kiefer-Wolfowitz with like sine waves, you can actually you get 1/t with bias, with epsilon squared bias for smooth functions, and then in order to get no bias, there would be a loss, and I don't really know yet how much, but I don't know why you would use white noise for stochastic optimization if you have full control of the noise. That was really my point. It wasn't really a question. Okay.
Well, I guess maybe it's also related to the lower bounds, right? That if you only have this point evaluation property, then maybe a deterministic method is actually going to do better than if you're just inducing some noise. Yeah. In terms of estimating gradients, I guess there it's like was maximum seeking, and then there you saw the advantage. I don't know whether you can see the same advantage shown just estimating the gradient. Yeah.
Excuse me.
So the advantage in maximum seeking that came from this quasi-random point of view, is it can it be traced back to just the variance reduction with same?
Well, it's just a different culture. The extremum seeking control, that literature was just like a completely, I don't think that many of the people, they didn't know about Kiefer-Wolfowitz when they developed that theory. And I'm not sure, if we were maybe the first to point out that they were related. I don't know. I'm still trying to work out the history. But it was like two different, it was like another planet, the extreme seeking control.
Right, I guess I'm wondering whether this quasi-random inputs would, like you can see them as improving the quality of the gradient estimates. And that's why Kiefer-Wolfowitz improves.
Yeah, well, that's after the fact for sure, that's why. Basically, like a sine cosine is a Markov process, but with covariance 0. And so you lose some terms when you do the rate analysis. So it's any Markov process with 0 asymptotic covariance would be a big improvement on using IID exploration. That's really what it is. And that's why you do the same analysis you do for a stochastic approximation. Yeah, so I wonder what you get if you really want 0 bias. You probably don't get 1/t, but I bet it's a lot faster than 1/t to the 1/3. I bet it's yeah.
Okay.
That'll be interesting.
To look at it.
Yeah.
I guess we have to wrap up because we are quite a bit over time, and we are starting to grab the time of the next talk. Yeah. Thank you, Peter, again.
Thank you very much.
It was very nice to have you. Very much enjoyed the talk. And if we are looking for the final versions of the slides later, and keep in touch.
I will. Thanks for all the great questions, everyone.